Hello, we're going to be talking about solving equations today, and we're going to be looking at solving equations that have exponential or logarithmic expressions inside the equations. We're going to be learning some algebraic techniques that we can apply here, and we'll be reviewing some of the calculator techniques that we've already learned for finding approximate solutions. Okay, so let me first say that these techniques are pretty limited. They only work in certain kinds of equations. But if we have just logarithms and they're all the same base, we can use some of our properties of logarithms to manipulate the equations around and the expressions in the equations around and eventually solve for the missing variable. And if our exponent is up in the our exponent contains a variable, or the variable is up in the exponent, sometimes we can apply logarithms to that equation and pull that exponent down. But if we have some other situations, these techniques don't work. For example, if you have a mixture of power functions and exponentials, or exponentials and logs, or in fact if you have kind of different kinds of equations kind of mixed together, like polynomials and exponentials, or polynomials and logs, logs and exponentials, any of those kind of combinations, usually the techniques that work for one of those subparts will not work altogether, and so we're basically forced to use some calculator approximation techniques. And of course, if you're only interested in approximate solutions, the calculator techniques are just as good anyway, and we don't need the algebraic techniques. But there are some algebraic techniques we can use in some cases, and we're going to look at those. So we're going to talk about first solving equations that contain some logarithms. And again, these are probably going to need to be the same base logarithm, or you're going to need to use a change of base formula to get them to the same base. And so the idea is to get all the logarithms on one side of the equal sign by adding their opposites if you need to eliminate some. Combine them into single logarithm using our properties of logarithms. Of course, then they're going to have to be the same base. And then rewrite the logarithmic equation as an equivalent exponential equation. And then hopefully at that point we got something simpler and we can go ahead and solve that. So here's an example that we're going to work with here. So we have 3 times log base 2 of x equals, or minus 5 log base 2 of 3 equals 11. So the logs are the same base, so it looks like there's some hope that we might be able to get this to work. But we can't, the idea is to combine them together, but we can't do it the way they are because the coefficients have to be 1 or negative 1. So we first take care of those coefficients by bringing them inside the logarithm, and when they come inside the parentheses there, they become exponents on the inside. So 3 log base 2 of x becomes log base 2 of x cubed. And 5 times log base 2 of 3 becomes log base 2 of 3 to the 5th. Now they're both logarithms the same base, and they just have coefficients 1 or negative 1. We can combine those into one single logarithm, base 2 of course, and then we have x cubed over x to the 5th, 3x to the 5th. Notice that the 3x to the 5th, that logarithm of that, had a negative 1 in front, so the 3x to the 5th goes to the bottom as a factor there. And the x cubed had a positive 1 in front of that logarithm, so the x cubed goes to the numerator as a multiplication, as a factor there. Okay, so now we have a logarithmic expression. A single log equals a single constant. Okay, we can rewrite that as a exponential. The base is the base either place, so we have base 2 for a logarithm, so we have base 2 for exponential. 11 equals the logarithm, so 11 is the logarithm in the next line. That is, 11 is the power, it is the exponent. And then the other side of the equation is x cubed over 3 to the 5th. Now we actually know how to solve this from our earlier techniques. Multiply both sides of the equation by 3 to the 5th. That isolates x cubed by itself to get x cubed equals 2 to the 11th times 3 to the 5th. Then we can take the 1/3 power, or the cube root of both sides, and now we have it solved for x, but we want to sort of rewrite that in a reduced radical form on the right side. So if you remember, what we do is we take the powers and we divide by the root. So 11 divided by 3 is 3 remainder 2. So the remainder 2 remains in the radical on the base of 2, and the 3 quotient goes outside the radical as the power on the base of 2. Similarly, we take 5 divided by 3 is 1 remainder 2. So the 1 is the power on 3 on the outside of the radical, and the 2 remains the power, the remainder remains the power under the radical on that base of 3. So now the powers under the radical are less than the degree of the radical. Can't reduce that radical anymore, so let's go ahead and multiply out. 2 squares is 4, 3 squares is 9, 4 times 9 is 36. On the outside, 2 cubed is 8, times 3 is 24. So we get 24 times the cube root of 36, which is the exact answer. Now, I can figure that out approximately on my calculator as 24 times 36 to the power 1/3. So I need to do it as a fraction power on my calculator. And hopefully that's what I have here, 79 point whatever. Okay. So I'm going to bring that over here. Okay, so now how could I have done this on just a calculator technique? So once again, if I want the exact value, I have to do it the way I just did it. There's no way to get this without using this basic algebraic technique. And if we want it expressed as a reduced radical form, then the exact answer is 24 times the cube root of 36. Okay, if we want a decimal approximation, we're going to need a calculator at some point, and we came up with the final answer of 79 point something. Now, if we just all we need is a 79 point something, we don't have to do this algebraic technique at all. We could just find that directly. Now, we do have to do a little manipulation, however, because we don't have a log base 2. So, without a log base 2, we're going to have to rewrite this expression. And if you'll look, you could rewrite it. Actually, got it rewritten here. Rewrite this as 3 ln of x over ln of 2 minus 5 ln of 3 over ln of 2. And then I subtract 11 and it equals 0. So I left the left side of this be f of x, or y1 of x. And then we want to see when that's equal to 0. That's when it crosses the x-axis. That's a calc 0 in our calculator. Okay, calculate the root, or 0. And so we put that in here. 3 ln of x divided by ln of 2 minus 5 ln of 3, make sure we close all the parentheses, divided by ln of 2, and then minus 11. Okay, and so that's our expression. Let's go ahead and pull that over here. Alright, so there's our first calculator screen that we're going to have. Clean up the formatting a little bit later. Okay, and then where do we go from here? Okay, so we want to graph this. Okay, and we need to choose an appropriate window. Now, since I already have the answers about, close to 80, I need to go on out pretty far. I know from the start, though, that I've got a logarithm of the x. So the x can't be negative or 0. I can eliminate that right off the bat. So I might as well start my x window at 0 and then go to the right, and let's say we just go out 100, mark it off in tens. Now, I'm wanting to see where this crosses the x-axis, so I'm going to put the x-axis right in the middle of the screen. So negative 10 to 10 for y actually is going to be probably pretty good. We may need to zoom in a little bit, but this should give us something that we should see. And hopefully we're going to see this crossing at about 80, about 79 point something. So we need to maybe a little trial and error. Now, if I didn't know ahead of time that it was, by working out this way that it was 79, I would have to maybe do a little trial and error, maybe look at the table. But I need to find some place where it crosses the x-axis there. Okay? And we did. So now I can, so let me bring that screen over for the notes. Okay, so we can see what we chose there for a window. And then we see the graph. And then on the graph, we want to calculate the 0, or the root. So you want to calc 0. Okay, and what does that turn out to be? Well, it asks us for a left bound, so we get over kind of close to it, but definitely on the left side. Hit enter. Make sure we're on the right side. Since this is an increasing function, through the axis there. It'll be positive on the right and negative on the left, so that's pretty good. We'll use that for our guess, for our bounds. And then try to get this as close as you can get it to 0. One of these guys here is probably as close as we're going to get right at the moment. So I hit enter for that, and that returns the value here. And notice if I go back and just quit and hit X, sometimes it'll even show me some more digits. But look at that. It's exactly the same thing we got before. So definitely it does seem to check. Now another thing that we can do, of course, is actually just store that as X, and then actually type in 3 ln of X divided by ln of 2 minus 5 ln of 3 divided by ln of 2. And this is just a straight out check by plugging it in. Unfortunately, and we should get 0 here, yeah, so it is checking. And of course, to do this, you do have to know your change of base formula, or you really can't get started very much with the calculator. Okay, let's alright, I'll clean some formatting up, get that on one page in a minute. Okay, so here's some for you to try now. Okay, so here's two different ones. They work a similar way. So you can do it whichever one you want to do first. You can either figure out a decimal approximation using your calculator first, and then come back and do an exact value, or you can do the exact value first and then the decimal value. But do it both ways. Do it with a calculator approximation technique and with an exact value using the technique we just talked about. When you get these done, come back and we'll check your answer. Press pause now. Alright, well, we're back, and this is the algebraic technique here. I'll just pull it up a line at a time. So the first thing, they're all log base 5, so that's good news. We want to combine those together. We can't do it like it is, so we have to pull those coefficients up and make powers out of them like this to make 5 log base 5 of x, log base 5 of x to the 5th. And this 2 comes inside where it becomes the second power. Now we have coefficients 1 and negative 1, so we can combine it. And that's log base 5 of x to the 5th over 3 squared. Rewrite as an exponential. The base is 5. 11 is the logarithm. That's the power. So we get x to the 5th over 3 squared is 5 to the 11th. Multiply both sides by 3 squared. And now we've solved for x to the 5th. Just take the 5th root of both sides, and now we've solved for x. So at this point we have the answer. We just need to clean it up. We could probably type it in right at this point here and get a decimal approximation if we need to. But we want to reduce radical here, so let's go ahead and do this. 2 divided by 5 is 0, remainder 2, so that one's going to stay where it is. 11 divided by 5 is 2, remainder 1, so that's 5 squared on the outside, 5 to the first on the inside. Now the powers on the inside are less than the degree of radical, so 3 squared is 9 times 5 is 45, 5 squared is 25 on the outside. And so the exact answer is 25 times the 5th root of 45. You know what I'm going to do? I'm going to make sure that that's clear, that that's the final answer by boxing it in. So that's the exact answer. The one below is the approximation. Let's do that up above too. So the exact answer, the final answer, was right here. Okay. Now, that turns out to be 53 point whatever here. Okay, let's check that with the calculator. So it should be 25 times 45 to the power 1/5. Be sure you put that 1/5 in parentheses. And hopefully that's the same number we just came up with, if I copied all the numbers over correctly. Okay, good. Looks good. Okay, so that's the first thing. Now, what if we were just to do it by hand? I mean, not by hand, but by the calculator. Well, we need to put this in our calculator. And it's 5 times log base 5 of x. Well, we do log base 5 of x is ln of x divided by ln of 5. Minus 2 times ln of 3 divided by ln of 5, which is log base 5 of 3. And then we're going to go ahead and subtract 11. Okay. Now, we can graph this. Actually, that same window I had before seems to work okay for that one. Notice again, I know that I can't have a negative x, so that's going to make that a little bit easier to narrow the window down a little bit. So once again, I just use 0 to 100 for x and negative 10 to 10 for y. I'm wanting this one to cross the x-axis, so x equals 0, y equals 0 is right in the middle of the screen. That worked out pretty nicely. Then I want to do a calc 0, number 2. Let's see, we're on the left side there. And then we go up to the right side, and then a guess. And there we have it. Again, if I just quit and hit X at this point, that's the same thing that I came up with a while ago. So that's our solution, at least approximate solution. Okay. All right, let's look at the next thing here. All right. How about another example? Very similar. This is natural logarithm, but same kind of thing. Bring the coefficients in, make powers out of them. Now we can combine it to one logarithm. Then we can rewrite it as an exponential. This time the base is e, so it's e to the 10th equals whatever's in the parentheses. Multiply by that denominator and you get the x cubed by itself. Take the 1/3 power or the cube root of both sides. I decided just to leave it in a power form this time, and then use a property of exponents to raise each one of these to the 1/3, which means we're going to multiply the powers, so we get 2/9 here and 10/3 here. I could have rewritten that as say a 9th root, or I can leave it as powers. So I'm going to just leave it there as powers. Again, this is the exact answer in the exponent form. Okay, and the approximate value is down below. Let's check the approximate value with the calculator. It should be 3 to the power 2/9 times e to the power 10/3. And sure enough, that's what we just came up with. Okay, continuing on. Let's see here. Okay, how could we do this one approximately on the calculator? Actually, this one in a way is a little bit easier because we don't have to use the change of base formula, because we do have an ln button. So we can type it pretty much like it looks. 3 ln of x minus, let's put that in parentheses, 2/3 ln of 3. And let's go ahead and just say minus 10 and see when that's equal to 0. So again, x can't be negative, so maybe this same window will work again. Yeah, I did. Okay, so let me pull that screen over here. And we want to calculate a number 2, a root. Then we'll go back to the left side of here. Okay, that's the left side for sure. Then we go to the right side. Okay, we're on the right side. It works better if you give it a guess. It's pretty close, but there we go. That's not bad. And it should come up with our value that we're looking for. That should agree with what we have above, and sure enough it does. Notice that you actually have a couple more digits up here. This one stops at this 874 at the end, but if I quit and just hit X, you'll go ahead and get those extra couple of digits there too. Okay? Alright, so now so those were equations that had had logarithms in the equations. And so remember the basic setup there was, let's go over the steps again. Get all the logarithms on one side of the equals, then combine them into a single logarithm using the properties of logarithms. Rewrite the log equation as equivalent exponential equation, and then hopefully you can solve that using some of our earlier techniques. Alright, how about this one here? Look at how we can solve this. Here we have an exponential. Okay, well what's the problem? We got the x is up too high, we can't reach it. We need to knock it down. How can you knock it down? Well, throw a log at it. Just throw a log at it, knock it down. Okay? So basically that's going to be this property of logarithms is going to allow us for that to make sense, where we have natural log of b to the x equals x times natural log of b. Okay? That allows us to bring that power down. So I take the natural logarithm of both sides here, and I bring the power down. Okay, so at the first glance it looks like I made it harder by sticking that natural log on both sides, made it more complicated. But in fact that logarithm acts as like a log to knock it down, a stick to knock it down, or maybe you think of it as a ladder to reach up there and grab it. And so the logarithm then applied to each side allows us to pull those powers down. Well, now it might not look like it, but actually that third line now is just a simple linear equation. It's just like 2x minus 5 times 12 plus 3x plus 4 times 7 or something. Of course, it's not 12 and 7. It's some irrational number, a log of 3 and log of 5, a log of 3 and log of 2. But it's just a constant. So this is really just a simple linear equation where you can use our simple linear techniques. You eliminate the x's on one side by adding its opposite. So we want to get rid of the x's on the right. We add a negative 3 ln of 2. Well, first we distribute. So we got ln of 3 times 2 times x is 2 ln of 3 times x. And then we got negative 5 times ln of 3. On the right, we have ln of 2 times the 3 times x is 3 ln of 2, which is our coefficient, times x. And then plus 4 ln of 2. Now, we want to get rid of the x's on the right, so we're going to add the opposite of the x term, negative 3 ln of 2 times x, add that to both sides. And then we want to get rid of the constant term on the other side, so we add 5 ln of 3 to both sides. Well, when this settles, the x's and all that stuff cancels there with the variable terms on the right. And the left, we get 4 ln of 2 plus 5 ln of 3. You can actually put those together. Right now I'm not going to. I'll do that as a later step. And the left, the 5 ln of 3's cancel out, and we get these two things added together with the x's. So the way you add those together is you factor the x out with the distributive property and add the coefficient. So the new coefficient is 2 ln of 3 minus 3 ln of 2. Well, now you just have some constant times x equals some other constant. You just got to divide both sides by the coefficient of the x to cancel out the 2 ln of 3 minus 3 ln of 2 on the left side, leaving x by itself. And now we have a solution. So actually, you could actually just stop right there. That could be your final solution. Okay? But there are other ways to write it. You might write it this way. Do you see what we did here? We actually wrote it as this is ln of 2 to the 4th. 2 to the 4th is 16. And this is ln of 3 to the 5th, which is 243. This is ln of 3 squared, which is 9. The 3 squared is 9. And then 2 to the 8th, 2 to the 3rd is 8 here. Or we could put this together. Another way we could write it is right here. So any one of these in boxes could be your final answer. If you type these in your calculator, they all turn out to be the same thing. We'll check that in a minute. So we got this by log of a plus log of b is log of a times b. So the 16 times 243 is 3,888. And here when you have a subtraction of two logs, it's a log of the quotient. So it's log of 9/8. 9/8 is 1.125. However, we cannot combine the last one into one logarithm. Well, I guess we could if we change the base to a base of 1.125, but there's no point in doing that. We want to leave it in base E logarithm. So we can't simplify the last one. So any one of these three would probably be acceptable answers. Now the thing you have to watch out for when you're working with, say, some problems in, say, in my math lab, or you look up problems in the back of the book, you know, I've had a lot of students do these, particularly in a calculus class, and you're in the middle of this big long calculus problem, a lot of algebra steps, and they come up with an answer, and maybe they got the answer this first box, but the book put the answer in the third box, and they think, oh, I missed it. Well, no, not necessarily. It's just the same thing in a different form. Or if you have a multiple choice question, and these are the various answers, you might need to check and see, you know, which one, because the right answer may be there even though yours is in a different form. Because these properties of logarithms make things look very different, but they're really not. We're just using different properties. Okay, so if I take that now, and let's do this a couple of different ways. First, let's evaluate this. And I'm going to actually type all of these in. Okay, so the first one, parentheses around the numerator, 4 ln of 2 plus 5 ln of 3, close the ln, close the numerator, divide by, that's your fraction, parentheses for the denominator, 2 ln 3, close that, minus 3 ln 2, close the denominator. Alright, that's one way we could get it. The second one, just to show you that it's the same, parentheses around the numerator, ln 16 plus ln of 243, close, divide by ln 9 minus ln 8. Same answer. Okay, that's the same thing both times. Okay, and what about the last one, which is actually the easiest to type in the calculator? ln of 3888 divided by ln 1.125. I'd probably say the last one was the simplified version, but they're all actually correct answers. Okay? Now, how can we check it? Well, we could check it by just taking that answer, store it as x. Now, what we want is both sides of the equation to be the same thing. So when I go back up here to the equation, the original equation said we have 3 to the power, parentheses 2x minus 5. Okay, that's way up there, 3.8 times 10 to the 64th. But as long as the other one's the same, we're in good shape. 2 to the power 3x plus 4. Good, it checks. And so that allows us to a way to check it. Okay, well, how about actually finding the calculator, finding it with the calculator? Well, a couple ways we can do it. We can do it two different ways. We can either, let's do it the second way, a different way than we did the last one. We can actually graph both sides. 3 to the power 2x minus 5 and 2 to the power parentheses 3x plus 4, and notice here x could possibly be positive or negative, so let's try to find a window. Let's go negative 100 to 100 to start with, and when we do 3 to these powers, we're going to get positive, so we might as well just start at 0. 3 to a power, 2 to a power, those are positive, and actually we got to go way up there. Because we know that the answer is like 3.8 times 10 to the 64th. You might not guess that right off the bat, but let's say we just put in 100 and graph this. The problem is these things are pretty close to each other for quite a while, and it's hard to tell. If we set our window big enough, we could probably get it this way. But we're looking for where they cross. But maybe a better way to do it is to do it the way we did the last one with logarithms. We just set it equal to 0. So subtract here. This is maybe a little bit better. One thing about this, you don't have to worry about the y scale so much, because you know the y is going to be 0 where that you're looking for. So if we just go from, say, -10 to 10, and we may need to zoom in closer than that. In fact, let me go ahead and do that. Let's just go from -5 to 5. And I'm still going to leave it like that from -100 to 100 right now. So now what I'm doing is I'm just looking for where this crosses the x-axis. Now I've got a feeling these are pretty close to each. Okay, so it's zooming up here somewhere, and then it's actually staying really close to the axis. Okay, now this says the answer ought to be 70 point something, so it should be on the screen, but it's hard to see it. Let me do a few traces here. If you look, we got negative y's, and then we have positive y's. So somewhere in between here and over here, it changed sign. See, we're looking at the y values. So even though I can't see it because I'm so close to the axis here, I need to zoom in way more than this to see where it's crossing. But anyway, as long as I see this negative to positive, that's going to tell me we're pretty close to where it's crossing. So I'm going to go ahead and go calculate a 0, and it looks like this thing is increasing as I go from left to right. So over here we have a y is negative, so I'm going to let that be my left bound. I'm going to go over till I see a sign change. Okay, there we go. Y is positive, so I'm going to enter that, and then I'm going to try to find whichever of these y's is closest to 0. Well, none of them are real close, but that's as close as we're going to get, and hit enter, and hopefully it's going to return a y of 0 now. Well, it did return the right value, but it didn't return a y of 0. That's kind of strange. Let me try this again. Let's go. So look, we're in the 70 range, right? So let's zoom in a bit. Let's go from about 60 to 80. Okay. And let's go in really close. -0.1 to 0.1. I can't even see it. Okay, not a good window. Let's try. Maybe we're way too close. Let's go. Yeah, because this thing's going way out there. Okay, so let's go -1,000 to 1,000. It might be a little better. Are we going to see any? This thing is changing. It's going so fast. See, we're way up there. Way up there. So we need to change the window actually to really, really, really big and really small. See, we still want the 0 right in the middle. So I need -1 and then say times 10 to the 100th power. And then, whoa, oh, we can't go 10 to the 100th power. 10 to the 50th power. So sometimes this is a little bit of a trial and error. And then 1 times 10 to the 50th power again. That's still going to leave the x-axis right in the middle. Now I'm trying to get to where I can actually see some of the graph. Yeah, you can see some of it. It still looks like it's almost vertical there. But at least we can kind of see where it's crossing. We actually see some of the graph this time, so that's good. So we want to calculate the 0 here. So x is negative, so that could be a decent left bound. The y is positive there, and we can let that be our guess. Okay, and we're still not getting very close to 0 here, but that is the right value that we need. So we're good. So there we go. Okay. Alright, so so there was our example. Now it's your turn to try a couple. So here are a couple to try here. So again, I want you to get a calculator solution. I also want you to get an exact solution using these algebraic techniques. Exact solution is probably going to have some natural logs in it, and your calculator solution, of course, will have a decimal value. So go ahead and work this out. Come back and check your answers with me in a few minutes as soon as you finish. So press pause now. Alright, so here what we do, we've got to get our hands on the power, so we take a natural logarithm both sides, bring the powers down. They become multiplications, so that gives us 4x times natural log of 3 equals 2x plus 3 times natural log of 5. Distribute, so that gives us 4 times natural log of 3 times x on the left, 2 times natural log of 5 times x, plus 3 times natural log of 5 on the right. Subtract 2 natural log of 5 times x from both sides to eliminate it on the right, and on the left factor the x out, and that gives us 4 natural log of 3 minus 2 natural log of 5 as the coefficient of the x. Divide by that coefficient of the x, and this is one of the ways you could write the exact answer right here. So that could be a final answer. We could also, of course, apply our properties of exponents there. Okay, if you're going to do that, you probably might as well at least go to this version. Right? 5 to the third is 125, 3 to the fourth is 81, 5 squared is 25. And in the bottom, you can combine those by making that 81 over 25, which in decimal form is 3.24. And I haven't figured out this yet, so let's try this. Now, if I do all these different versions and I get the same thing, then I know I haven't made any mistakes in my manipulation here at the end. That doesn't necessarily mean I solved it correctly, though, because I still have to check it in the original one. But hopefully I've not made a mistake. We'll find out in a minute. But I'm just going to put the last one in here. And this should give me a decimal approximation. Okay. 4.11. Uh, 4.107199.113. There we go. So there's a decimal approximation for it. Alright, let's try a calculator technique. Now this one I bet we can do with the calculating intersection method. Let's try it that way, since we haven't illustrated that yet. 3 to the power 4x and 5 to the power 2x plus 3. And let me just start with a zoom standard, and we'll go from there. Well, I'm sure we'll most likely have to adjust it. So there's an exponential, and then we have 2 exponentials. Okay, there they are. Turns out they don't. It's hard to tell. They could cross over here in the negatives, but they don't. Okay, and let's see what happens here. We need to go up higher to see where they cross each other. So let's go up quite a bit higher. Looks like it may happen on screen horizontally. Just got to go up higher. So let's go up a couple hundred here, and maybe mark off in tens and see if that See if that gets us any better. Hard to see. So here's where it probably is better to go ahead and do, probably if I experiment with this enough, I could get a correct looking window. It's probably easier to go ahead and use the Calc 0 method. So I'm going to go ahead and do it that way. So get it all on one side and then 0 on the other side. So 3 to the power 4x equals 5 to the power 2x plus 3. And this time I want to find where it crosses the x-axis. So put the x-axis in the middle. So negative 10 to 10 perhaps. And we'll just try it negative 10 to 10 on the y and see what happens here. Trouble is they're going to be real close to each other here. It comes down and takes a turn, which we can't really see, and then it crosses right here. So right here, 1, 2, 3, 4 point something, around 4, that's going to be where we're looking for. So we want to calculate the 0. Okay. And okay, I can't see the cursor, but I'm also looking at the y values here. Y values are still negatives, positive. Okay, so it's between those two. So I go back to the negative, left bound, the positive, right bound, and pick whichever one of them is closer to 0 for the guess. And there we go. That x value should be the right one, and sure enough that agrees with what we did a while ago. So we're in good shape. Maybe not the best window, but it worked. Let me do it again so I can pull the screen over while I'm thinking of it. Okay. Alright, how about our next example? It's very similar. Take the natural log of both sides, pull the powers down, distribute, eliminate the x's from the left side by subtracting 2 ln of 5 times x, eliminate the constants from the other side by adding 3 ln of 3 to both sides. That gets you what we have here. Combining like terms there on the left by factoring the x out, adding the coefficients, divide by that new coefficient, and now we have our answer. Again, we could have left it like this. That's the first one we really came to. Maybe that's a good way to do it if you're just writing the answer down. But you can also use our properties of logarithms to bring each one of these in as a power and rewrite it like that. And then go ahead and expand out what those powers are. That's the equation we have right there. The top we've got 27 times that big number, which is this 2 million something down here. And the bottom we're dividing, actually that's the same one we had a while ago, 81 over 25, which is 3.24. So there's the exact answer there. And that's 12.38 something. So let's check that. Okay. Now let's just show you could just check it without doing, if you've done this. So we could do log of 2109375 divide by natural log of 3.24. Now hopefully this is the number I have there. Okay, I'm going to store that as x. Now if I go back up here and just type in my original equation, type the left side, type the right side, I should get the same thing. So if I put in 3 to the power 4x minus 3, I'll get something, probably big, 1.6 times 10 to the 22nd. But if I do 5 to the power 2x plus 7, I should get the same value, hopefully. Yeah, good news. So that actually did check. And so that's how you can compute the decimal approximation and check it on your calculator. Now, if you actually had to just find it from your calculator, well, what are we going to do? Well, again, we're having a lot more luck with the this method here where we solve for 0. So let's go back up here again. Where's my equation? There it is. So I'll put that in. 3 to the power 4x minus 3 minus the other side, 5 to the power 2x plus 7 okay, and let me try the window here. Let's see what we might do. Well, we'll just start with the zoom standard and just go from there. See how we might have to adjust. This is probably a horrible window. Well, it looks like it could be crossing over here in the negatives, but that could also be an asymptote. It may or may not turn around. Let's see what the actual answer was. 12 point something. Okay, horizontally it's on the screen. No, it's off the screen. Our screen doesn't go quite far enough out. So, turns out that from 0 to 15, that ought to pick it up. Let's see if we can see. So it should be crossing here around 12, right in here. If we can see it, can't see it because this thing probably is way out there. Let me go from negative 10,000 to 10,000, marked off in thousands. Alright, let me see if I can, let me just hit a trace and see if you can see we can see anything. Okay, we're getting some values there, negative, positive. Okay, so let's see what happens. I'm just tracing over. All these values are negative. See, I'm looking at the y values, they're negative. Even though I can't really see them on the graph, they're off the screen. Negative, negative, still negative. Negative. Should be turning positive pretty soon here. Negative. Oh, positive. Okay, so right in there we've got somewhere in there we got an answer, because if it's negative on one side, positive on the other, we know it's continuous, so it's got to cross the axis somewhere in between. So here I'm going to go to the left side. Left sides were negative. Okay, there's negative. Then the right side, it's got to be where it's positive. There it's positive. I'm going to use that as my guess too, and let's see what we get. Yeah, so we get a y of 0, and there's our x. And we did that with, unfortunately you can't see it very well. It's either real close to the axis or it's just growing, well actually it's growing real fast. It's almost vertical, and the points are all the way off the screen, so it's not showing it very well. But, didn't matter, it actually did it numerically, so we were okay. Okay. And we were able to compute the answer we needed. Okay, so that gives you some examples. Let's just review the algebraic techniques. If you have logarithms, get all the logarithms on one side of the equal sign, combine them into a single logarithm if possible using our properties of logarithms, rewrite the logarithmic equation as an equivalent exponential equation, solve that resulting equation. There are several places this could give you problems. If the logarithms can't be combined for some reason in a single logarithm, then this technique's not going to work. Or if the resulting equation you get at the end is not something that's solvable by other techniques, you're in trouble. In those cases, you have to resort to an algebraic technique. Okay, if we're talking about exponential equations, you isolate the exponential expression, take the natural logarithm of both sides of the equation, use the property of exponents to grab that exponent and bring it down. Now you're no longer got exponential equation, no longer got the variable up in the exponent, solve that resulting thing. Now finally I just want to mention that there are equations, again, that these techniques don't work. For example, something easy we've already looked at was x to the fourth equals 4 to the x. That has a solution in the second quadrant that just is just can't be found with the techniques that we use for power functions. It can't be found using the techniques for exponential functions. Or if you had a logarithm and exponential, then the same thing. Like if you had log of x equals 3 to the x, that's not going to be something that we can solve algebraically very easily. Okay, so you may need to use some sort of graphing techniques or algebraic techniques or calculator techniques. But the calculator techniques we've learned and we've shown here actually are pretty widely applicable. So keep those in mind. If you only need an approximate answer, a decimal answer anyway, you might as well just do those. But if you need exact answers, now we have some techniques that work in at least some situations.